Hello everyone, today we will be talking about the DC behavior and continuity of reactive elements. A little recap since I didn't make any YouTube videos about the equations shown here on the screen, but we can calculate the capacitance of a capacitor if given the permittivity area and distance between the plates of a capacitor. We can calculate the capacitance of series capacitors as well as parallel capacitors. We can also calculate the current of a capacitor, which is C times the derivative voltage with respect to time of said capacitor. And the voltage of a capacitor is equal to 1 over C times the integral while considering the initial current, initial voltage of the capacitor. Now, for those who are visual people, this is a drawing of a capacitor with the current going downward and the voltage of the capacitor shown with its terminals. Now, with respect to inductors, we could calculate the inductance of an inductor by knowing the permeability, the number of turns squared times the area of one of those coils, and divided by the length of the inductor. We could calculate the series and parallel equivalents of an inductor, and we can calculate the voltage of an inductor, assuming we take the derivative of its current function, and we could calculate the current of an inductor explicitly by doing this integral and considering the initial current of the inductor. And this is a drawing of an inductor with the shown terminals of said inductor and the current flowing down and the voltage across said inductor. Now, let's talk about the DC behavior of these components. I don't actually like the terminology DC behavior. The terminology that I would rather use is DC steady state SS behavior of caps and INDs, which means inductors. First and foremost, we have to understand that DC steady state means all voltages and currents in a circuit are constant and ongoing persistently with respect to time. In other words, what does that mean? To be very specific, the derivative of any function with respect to time is equal to 0 when in DC steady state behavior. Okay? Again, DC steady state behavior means that all voltages and currents in a circuit are, what did I spell there? All voltages and currents in a circuit are constant and ongoing persistently with respect to time, which, in other words, mathematically, the derivative of any function with respect to time is equal to 0 when you are in DC steady state behavior. I'd also like to write whoa, what is up with my iPad? Sorry, y'all. 1 second. Common phrases used to show and state when a circuit is in DC steady state behavior. For a long time means DC steady state behavior, and as time approaches infinity. That's another common terminology used to show that a circuit is in DC steady state behavior. Okay? So, what is the significance of this with respect to capacitors and inductors? Well, Caps in DC steady state behavior will become open circuits. Again, in DC steady state, current is equal to, the current of the capacitor is equal to C dVct dt, which is equal to 0. If there's no current through the capacitor, it behaves like a open circuit. Open circuit, no current flow. Again, there's no current flowing down or across the capacitor. What about inductors in DC steady state? They will become a wire. Why a wire? Because an inductor in DC steady state, the voltage across the inductor is equal to L times the derivative of the current, which is equal to 0. Because the function with respect to time went to 0, just as above, right? So if the voltage drop across the inductor is 0, you can replace it with a wire. Wire, no voltage drop, no voltage drop. All right? Now, moving forward, what do we mean with continuity? Before we talk about continuity, let's talk about switching. So let me just make sure I'm aligning things. Yeah. Switches. Okay. A switch allows us to go from, let's say, position A to position B. And it happens at some time in this class or notes, it's usually at time equal to 0. So, at time equal to 0, switch goes from position, no, so it's not position B, it's just, there you go. It goes from position A to midair. Okay, think of it like that. Now, at t equal to 0 minus, switch has been at position A for a long time and is so close to being switched to midair. Okay? Again, at t equal to 0 minus, switch has been at position A for a long time and is so close to being switched, but is not switched yet. Why? Because it happens at t equal to 0 minus. t equal to 0. Similarly, at t equal to positive infinity, okay, switch has been at mid-air for a long time. Okay? Those are the three takeaway messages when we talk about switches. Now, the opposite could be the opposite can be true. For example, I could have had a switch that was there you go. Let's try to make that cleaner. Now here, what's going on? At t equal to 0, switch goes from mid-air to position A. Correct? The arrow shows that we're going to go to position A at t equal to 0. But at t equal to 0 minus, switch has been in mid-air for a long time and is so close to moving to position A. And then at t equal to plus infinity, switch has been at position A for a long time. Okay? Those are the important things to consider when we're talking about switches. Now let's talk about continuity. Continuity. When caps and inductors are in switch-related circuits, a sudden flow of current and voltage, respectively, will flow along across them. Right? You don't have, I'm not going to draw it, but if you've seen capacitors or inductors in a circuit that has a switch, all of a sudden voltage or current is appearing in the circuit. But one thing we have to remember is, however, I can't spell something. However, for capacitors, VC of t must be continuous and therefore not change abruptly with respect to time. Why? Because the current of a capacitor is equal to the capacitance times the derivative of the voltage. Therefore, if VC of t is continuous, then IC of t exists. Otherwise, if VC of t is discontinuous, a discontinuous function, then IC of t, let's draw it a little cleaner, IC of t does not exist. Now with inductors, the current of an inductor must be continuous and therefore not change abruptly. With respect to time. Because VL of t is equal to L DIL dt. Therefore, what? Therefore, IL t must be continuous. Must be continuous so that VL of t can exist. Otherwise, if IL of t is not continuous, VL of t does not exist. Therefore, the takeaway message with this information is that the voltage of a capacitor is continuous and it does not change abruptly. For inductors, IL of t must be continuous and there is not a change abruptly with respect to time. Okay? Now, let's look at DC steady state behavior and the continuous behavior and understanding in an example problem. Sorry for the tongue twisting. This is an example. Why is it not going down? Whatever. Example number 1. Okay. Let's say we have a current source pointing up. We have a switch here. And it's going to open at time equal to 0. And we have a capacitor. And we're going to, I'm going to call this C, and this is the voltage of my capacitor. And this is my, let's call this IS of t. Okay. And for the first question, assuming switch has been closed for a long time, what is VC of t? More specifically, the way you could reword this question is, what is VC of t equal to 0 minus? Because the switch has not yet opened. So, solve this problem. Steps. Number 1, we're solving for the voltage across the capacitor, and it has not yet opened. So we are currently prior to t equal to 0. Well, realize that the question said switch has been closed for a long time. So we can assume circuit is in DC steady state since we are at t equal to 0 minus. The switch has been closed for a long time. Switch has been closed for a long time. Okay, so let's redraw our circuit. And I'm going to call this VC of t equal to 0 minus. From drawing, you can see that what? Cap is in parallel to a short circuit because the switch is closed. Again, this is for t equal to 0 minus. Therefore, the voltage across the capacitor is equal to 0 volts because it's in parallel to a short circuit, which is 0 volts. Question number 2. Okay. Question number 2 reads, switch is now open. Find the voltage across the capacitor at 30 milliseconds. Okay, and assume I is equal to 2 milliamps. C is equal to 5 microfarads. Okay, so the switch is now open. Find the voltage across the capacitor. Okay, steps. We're finding the voltage across the capacitor at 30 milliseconds in units of volts. Well, from my formula that I spoke about at the very beginning of this video, VC of t is equal to 1 over C, integrating from some initial time to some time of the current capacitor formula plus some initial voltage. Well, the initial voltage in this problem was 0. So this is just 0 volts. Now, VC of t is equal to 1 over C. Now, we can actually plug in values. C is 5 microfarads. And I'm integrating from, what's the time initial? 0. Time initial is equal to 0, because that's when the switch opens. And what's my t? 30 milliseconds. So 0 to 30 milliseconds. And I'm integrating over what function? 2 milliamps. With respect to some dummy variable. And we can do this integration. VC of t is equal to 1 over 5 microfarads. This would be 2 milliamps times some time, evaluated between 0 seconds and 30 microseconds, which gives you what? It'd be 2 milliamps times 30 milliseconds divided by 5 microfarads. And if you do the unit analysis correctly in your calculator, you should get 12 volts. This is not VC of t, this is VC of t equal to 30 milliseconds. 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 There you have it. So recap. The switch is now open. When did it open? At t equal to 0, as shown in the original problem statement. T equal to 0. Switch is now open. Find VC of t equal to 30 milliseconds, given that the current is 2 milliamps, the capacitor is 5 microfarads. At our t initial is 0 seconds, and our t of interest is 30 milliseconds. We know the formula for the voltage of a capacitor is equal to this equation shown here. I'm just plugging and chugging, and then I use my integration formulas that I have in my mind. Integrating 2 milliamps is 2 milliamps times time, evaluated between 0 and 30 milliseconds. I plug and chug right here. I complete my calculation on my calculator, and I get VC of t equal to 30 milliseconds is equal to 12 volts. Cool. And then I'm told, so for our circuit people, what does this circuit look like? Well, we have the current source. The switch has been open, and we have a capacitor. Okay, where IS of t is equal to 2 milliamps. That's what we got. Now, third question. What is the power of the capacitor at time equal to 30 milliseconds? Okay. We are solving for the power of the capacitor at t equal to 30 milliseconds, which has units of watts. How do we do that? We recall that P is equal to V times I. More specifically, power of the capacitor as a function of time is equal to the function of the voltage times the current of the capacitor. And if we look at our circuit, we can notate that VC of t equal to 30 milliseconds, that the voltage of the capacitor at 30 milliseconds times what? The current that's going through the capacitor is none other than the current source. So it'll just be IS of t at 30 milliseconds. That's going to give you the power of the capacitor at time equal to 30 milliseconds. Which is what? 12 volts times. If you go back in your problem statement, the current source is a steady current source. It's 2 milliamps at all times. So 2 milliamps. And therefore the answer is 24 milliwatts. That is the power of the capacitor at time equal to 30 milliseconds. Alright, that's all you need to know about DC steady state and continuity of reactive elements. I'm not going to do an example of an inductor because I don't have one to do. But to prepare for the next video, to get you thinking about the next video, realize how in this circuit at hand, we had no resistors. What happens when we incorporate resistors into our circuit? Stay tuned for the next YouTube video. Thank you.